Hey guys, in this tutorial we're going to look at how to create this object here. It's a test project I worked on quite a while back, and so the basic logic behind it is to divvy up a surface into a series of triangular panels and then map these three-pointed stars to each triangle. Alright, so we're gonna dive into Grasshopper, and we're gonna start by building one of these individual triangles, and then we'll map it onto a surface. Alright, here we go. So we're gonna start with a polygon, and we'll grab an integer slider, set it to a maximum of 6, but I'll set the actual value to 3, and then we'll plug that in. And so here is our base triangle. Now we're going to take that triangle and we're going to explode it. So when we explode a curve piece of geometry, we get two outputs. We get the curves, which make it up, and we get the vertices, which make up those curves. And so what you might actually notice is that we get 4 points despite only having 3 corners. And the reason for this is very simple. Whenever you have a closed curve, there will be 1, 2, 3, however many points, and then there will always be one more point which is going to close off that piece of geometry properly. So for this three-sided shape, there are 4 points. Okay, so what we need is we only need 3 of them. And so we'll just take a look at the list of points to see what's going on, and you'll immediately notice that the first and last point are exactly the same, which means we need to get rid of one of them. And we can do that using a cull index node. So we'll plug our list of vertices into the list parameter here, and it's asking for a culling index. And so what we need is to either get rid of the first item or the fourth item. So instead of typing, we'll get rid of the fourth, but instead of typing in 3, we're going to use a little trick. By typing in -1 in the culling index, it will automatically get rid of the last item in that list, which might not be very useful for this particular instance, but if you ever have a list that you don't know how long it is, and you just want to get rid of the last item, that's how you would do it. Alright, so next we want to get the center point of this triangle. And so what we could do is we could either use an area component, and an area component asks for a piece of geometry as its input, and it'll give you the center of that piece of geometry. But I prefer to use an average component. An average component is much more computationally efficient, nowhere near as heavy as the area component, and all it asks for is a set of numbers or a set of points, and it'll compute the exact same thing. You can see it sitting right on top of that area component. So we're going to get rid of that. Okay, and so next we're going to we want to get a point halfway along each of these line segments. So we're going to do a similar thing in order to do that. We're going to take each of these segments and we're going to explode them, and then we're going to use another average component to find the middle point of these 2 vertices for each of those curves, and that will give us 3 midpoints. Next, we're going to create a line from the center to each of these points. So that gives us 3 lines right there. And and then we are going to evaluate this curve. And the reason we're doing this is so that we can create a sort of an openable aperture. Remember to always reparameterize the curve so that your curve space basically exists from 0 to 1, and you can just use one of these 0 to 1 sliders to find any point on the curve which you choose. So next we're going to take this point and connect it to the two endpoints of this curve. And we can do that because we already exploded each of these segments, and we should have 3 lists of data, each with an endpoint of a curve. So we'll use another line component, and we'll use these points as our start point, and these points as our endpoints. And so there we go. That is the basic shape created, or at least the 2D representation of it. Now we'll just hide all of this geometry for now, just so we're only looking at this. You can see that this parameter will enable the aperture to open and close. So the final thing to do is to turn this into a solid piece of geometry. And so the way we can do that is using a very simple extrude point component. And so this will take any basic curve geometry and extrude it all to a single point. So we just need to give it a point value. And for that, I'm going to use a construct point node, and I'm going to plug that point into P. I'm also going to plug a value into Z. And so that gives us the top of our star, and we also want it back to the star as well. So we're going to add a negative component in here, and we'll just plug the negative and positive value into the Z, and you might notice a little bit of a problem here. And so the way we're going to resolve this, basically what it's doing here is it's trying to match the data structure. So there's two curves in every list. So one curve is extruded upwards, the other one is extruded downwards. So a simple fix for this is to just join the curves together. We're also going to shift the paths back to sort of deconstructs our hierarchy a little bit. And so now we have 6 curves joined into one closed curve, and that will be extruded both positively and negatively. And now we can use a break join component in order to make this into a solid piece of geometry which we have full control over of its height. I'll just hide all of this. So we have control over its height and over the openness of the aperture. Alright, so now how do we get this to map across a surface of some sort? Well, it's pretty simple actually. I'll start by creating a curve. So I'm just going to go into one of my vertical views, and I'm going to construct a simple wobbly curve of some sort. Go back to our perspective view, and we'll bring that curve into Grasshopper. We'll set that curve, and then we are going to use a pipe. So your standard pipe just asks for a base curve and a radius. We might make this a little teeny bit more interesting by using a pipe variable. So this asks for a curve, and it also asks for a curve parameter. So if any time we're asking for a curve parameter, we're going to reparameterize it, so we can just use our 0 to 1 slider. I'm going to make 4 copies of Actually, before I make those copies, no wait, hold on. Okay, those are going to be my 5 parameters. 4 and 5. I'm also going to make 5 radius values. And a radius we might want to have a max value of, I don't know, let's set it to 20 for now. And we'll also make 5 copies of that. And you'll notice our variable pipe component turns red at the moment, but as soon as we plug the correct number of inputs in, we're away laughing. Alright, so now we're going to set these parameters to about where we want them. I want one at the start, one at the end, and then several sort of midway along that curve. And then I can set my radius. So a nice fat bottom. Maybe I'll taper it a bit in the middle, do something a bit strange with it, and then we'll get it to stay at about that thickness, and then we'll make it pop up a little bit more. Actually, I'm not really liking how that bottom sits, so I might just adjust it a little, and let's see, yeah, somewhere about there. Alright, so that's our surface. We'll hide that curve. Actually, no, we'll keep the curve there for now. So the next thing we need to do is we need to create a triangular grid. And so grids are found under the grid tab in the vector, under the vector tab, and we want to create a triangular grid. So you can see there's our triangular grid. We'll add some integer sliders for the amount of triangles we want. So I'll set this to a maximum value of 20, and I'll make 2 copies of those, and we'll set a number for our x and y. Okay, now we're going to use a bounding box component. A bounding box basically finds the, I'm just going to hide this. A bounding box makes a box around any piece of geometry, it will fully enclose any piece of geometry you give it. And so at the moment, I basically want to make a box around all of these triangles. So I need to flatten this output, and you also notice that my bounding box is per object. I want it to be a union box. And so there we go, we have one box which encompasses the entire selection of triangles. And now I want to use a map to surface component. So map to surface asks for a curve to map. We'll plug in our triangles. It asks for a source piece of geometry for the coordinate space and a target coordinate space. So our target coordinate space is this variable pipe, and our source is going to be this. And so there we go. There are our triangles mapped onto the surface. Now I'm gonna mess around with my sliders to get just about the look that I want, and you know what? I'm happy with that. That'll do for me, so I don't need to worry about these anymore. Alright, so now let's see what happens if we take all of this and we plug it, we feed them into each other. Ooh, accidentally edited that, but we don't need to worry about the polygon, because basically these are all our new polygons that we're working with. Ooh, okay, it's done something a bit funny. Let's see where exactly it messes up a bit. We'll check the curve join, and we can see there's a little bit of a problem there. Let's check these lines. Okay, So it looks like these lines are all converging over here somewhere. And so why might that be? Let's go a bit further up the hierarchy. So we take this list, we find a whole lot of averages, and let's see, it looks like this might be our problem here. We have a mismatch in the data structure. We're just going to check that using a param viewer. So here we have 66 branches, and here we have 198 branches. So it looks like for every single list that we have here, we get 3 lists here. So we have 0, 0, 0, 0, 0, 0, 1, 0, and here we have 0, 0, 0, 0, 0, 1, 0, 2, 0, 0, 1, 0, 0, 0, 1, 1, and so on and so forth. So what we need is we need to turn this list here into a set of, we basically need to collapse this last stack. And so we can do that using a shift paths component. And so when we do that, we should now get 66 branches, each with 3 items. Okay, now we'll connect that into our line. We'll turn that off, and we'll see. Okay, it looks like our line is working a bit better there. We'll check the next line. Oh, okay, so once again, we get a bit of a mismatch going on. And so, once again, we'll check our data structures. So we have 66 branches there, and with this component, we have 198. So once again, we need to shift those paths, and we'll plug that in. Okay, so still doing something a bit weird, but it is getting better. You'll notice that now we're only getting, looks like we're only getting half of the curve. Maybe instead of shifting this path over here, what we need is we need to put each of these items on their own separate list. So the way we do that is we use a graft. So we'll reconnect up our vertex value here, and we'll graft this input. And there we go. That is what we want to see. A whole lot of stars across our surface. Cool. So as you can see, data structure is really important to get right. Alright, so now we'll move on further down the hierarchy, and let me just turn off these things that are all working properly. Let's see, the joining is working fine. The extrusion forms a bit of a problem. Now this was probably a problem we could have expected, because basically what we're doing here is we are setting our extrusion tip for every single one of these curves to a value, to a point which is over here. So everything is being extruded to this point, when in fact what we need to do is we need to create an extrusion point for each and every single one of these triangles. So what we could do is we could take, let's find where our center point is. There it is. We could find the closest point on a surface, and so we want the closest point from there according to this variable pipe that we created. So that will give us a point, and what we can also do is we can use an evaluate surface component. And when we evaluate a particular surface, this one here, we also need a UV parameter. Luckily, the surface closest point gives us that. So what this now gives us is a plane, and that is exactly what we need. We need some sort of idea about the direction in which these extrusion tips need to go. So we have that, and what we can do is okay, these are our planes over here. We need to deconstruct the plane, and we need to use the z-vector. The z-vector is the vector parallel, not parallel, it's perpendicular to the plane. So we need to move, let's see, where is it? Our average point based on this vector. Just turn all of these off, and I'm also going to set an amplitude. So we'll take this vector and we'll give it an amplitude, and like we did before, we want both a negative and a positive amplitude. So we'll plug in the negative, plug in the positive, and then we'll plug that vector into our transformation vector. And you can see as we slide this up and down, we get the corresponding back and front tips of our extrusion. And so before we plug it in to the extrusion tip, let's just check and see if our data structure matches up. We'll plug our move into here, okay, 66 branches, and we'll check our join. Our join also has 66 branches, so initial indication is that everything should work fine. Check our extrusion, and there we go. What do you know? It has worked flawlessly. And just for final measure, there are all our joined pieces of geometry. We can now turn these points off, as well as, what else do we have? Basically, we can turn everything else off now, because we're no longer worried. If we were to take this initial curve now, and turn the points for that on, and move them around, you'll see that our definition means that this surface will update accordingly. And that's really cool. Now we might just want to build one extra bit of functionality into that, which is how much these apertures open. So what we could do is we could maybe do something like, okay, this must be our aperture point. And so what we want to control is this parameter right here, how much the surface, how much the aperture opens or closes. I'll just drag that along. Okay, and so what we could do is we could maybe take this point over here, and we could check its distance to the curve, which makes the geometry. So we'll go curve closest point, and so these are all the points, and the curve is all the way here in the beginning. And so we should now have a distance value. And so that distance is, okay, we'll check what sort of values we're getting out of here. Okay, so our parameter is based on 0 to 1 value. So we need to get all these numbers and convert them to 0 to 1 values. And the way we can do that is with a remap numbers component. So we'll plug our distance into V. We're also going to get a balance component. The balance tells us what the upper and lower limits are of a list of data. But at the moment it's going to give us a whole lot of bounds because we have a whole lot of different lists. So we need to flatten this item here, and it tells us that our bounds are 4.59 to 8.44. So that's our source domain. And now we basically create our own target domain. Plug that into the transform, not into the transform, into the target domain, and we'll set two numbers to the start and end. And okay, so basically the closer something is to the central curve, the more open I want it to be. And the further away it is from the curve, the more closed I want it to be. So now we'll plug that into our parameter, and there we go. We now have these really nice closed apertures down the bottom, and they really open up in the middle, and then they do get a tiny bit, they do close off a tiny bit more towards the top, and this would all be controlled by our parameters over here. So maybe we'll just bump this last radii value up to maybe 9, and you can see that that change gets fed down the platform along Grasshopper, and there we go. That's our shape, or that's our geometry. I'll just do a quick pan through the definition for anyone that might want to just skip ahead across here, see anything that you might have missed. And there we go, that's it. That is our definition. Hope you enjoyed it.